All right, so Doug and I, yeah, so first of all, so my name's Kris, this is Doug. Callum and Greg are physicists, right? And they're different than engineers. And so
in other words, if we left it to the physicists, we would know a lot, but we would have never built anything.
Yeah.
Useful.
But
So we're going to
this
change.
is sphere.
So you're going to see that the tone of this talk is going to change a little bit. And this is what you get when you have two engineers who come up and start talking.
Yeah. So I'm Kris Dressler. I'm an originally mechanical engineer and sailor, and that kind of was what got me into fluid mechanics originally. And then years went by and figured out that kayaks are just a lot cheaper than sailboats. Practical, faster to get on and off water. And so that's kind of what put me here today. I also teach in the summers here with Rutabaga at the symposium and whatnot.
Yeah. Kris and I also have a common interest in fluid dynamics, and we'll talk a little bit about what that is. But my background is in fluid dynamics, and when I started paddling, I was instantly drawn in with the kind of challenges that you have in paddling, and it made me think about a lot of the physics that are happening. As I started getting some certifications and getting some instructorships things, I started noticing a lot of bad physics being talked about. But of course, I wanted to pass, so I just sucked it up and started like what's probably happening. But now that I get the podium, we're going to kind of debunk some myths that you may have heard from people. And we can kind of find there's a lot of soft science out there, and the internet has not been very helpful in helping
That's not right.
Yeah. So let's be clear, you don't need to understand anything that we're going to tell you to be able to enjoy paddling. And for example, if you're sitting on a plane and this is how you believe the planes fly, you're still probably going to get to where you want to go. The difference though is that when we're in a kayak, we're actually partly the pilot too. And so the pilot needs to probably understand a little bit more than that it's just magic and some more magic and these kinds of things. So this is actually a series of talks that Kris has been giving for some time. And to gauge the sort of interest of the crowd, he would start out with a slide that looks like this.
Yeah, so it's, like most of our, Doug and I spend most of our days kind of on this end, right? The Nancy left, right? Crazy math shit. And then, but other people are more on the horsies are pretty end of the spectrum. And that's good enough for them. And so the first time I did this at Door County, I just wanted to get a feel for where people are at. And most people were in, like, they were okay with some terms and maybe a Greek letter, but not much beyond that. So today we're going to keep it in like some terminology and stuff, not too many equations. One equation, a couple, maybe one or two.
Right, two equations.
But pretty basic, right? And because it should be fun, interesting. We're going to try to keep it 30 minutes or less, so we have lots of time to ask questions, right? In the description it said, if you got a question, bring it. And we're expecting all of you to have questions that you brought.
And actually this talk will conclude at a local bar. We're going to reveal the name of the bar at the end of the talk. So you have to stick around and decide where we're going to be.
And who's buying?
Okay, so let's start out. We're going to talk a little bit about what fluid dynamics are. So first thing, there's a lot of misconceptions. Fluids are both liquids and gases, and we're going to say that these are something that take the shape. So we're actually sitting in an aquarium of air right now. Air is a fluid. Now there's a lot of misconceptions with this because I think your grandmother told you to drink lots of fluids. So you're thinking that that's got to be a liquid. Or you're thinking I need more brake fluid in my car, and you're not going to stuff a bunch of air in there, or you're not going to go far. So the important things is that fluids take the shape. So this could be, everybody agrees that a fluid is a liquid, but we're actually in a big aquarium of air, and we're going to talk interchangeably about that.
So I can tip this thing all around, and the air adapts to where it fits, and then the water adapts to where it fits, right? And so they're both fluids, air and water, both fluids.
And the continuum idea is just that if I swipe my hand, I don't suddenly have a void of air. Air immediately fills what was behind my hand at the kind of speeds that I'm going to be doing.
So this is probably the most abused term in all fluid mechanics is Bernoulli's principle and Bernoulli this. Why does global warming is Bernoulli, plane flies Bernoulli, everything's Bernoulli. And so this is actually a little demo that we had of what Bernoulli's principle really does, and that is when you constrict the flow of something, when it has to flow through a small area, it has to go faster, and you can kind of see this whole thing go faster. And when that happens, the pressure actually drops. That is true, and that's about the limit of Bernoulli's principle. The faster it goes, the less the pressure.
So So all you're seeing here is that things are moving more slowly, start to move more quickly. The pressure's higher here and the pressure's lower here. So we're going to revisit those. These are important for understanding lift and drag. So we're going to set up two terms here, and we're not going to get big into the jargon. Lift is going to be simply something that gives us a benefit. It's going to move us in a direction that we want. We're going to leave the ground, we're going to propagate over to the side. We're going to be able to use that as a ruddering stroke. And drag is something that is going to be parasitic, or it's going to be counter to what we want. It's going to slow us down, it's not going to get us where we want to go. But as we'll see, it's sometimes a necessary byproduct of having lift. So you really almost can't have one without having the other. Are there any pilots in the room? All right. So you may have learned in pilot school that lift works because there's two particles, red and blue, here at the leading edge. And then these guys are going to leave each other, but they're going to meet back here at the trailing edge. Did you hear that theory?
No, in pilot school they debunked that.
Good. Okay. We have pilot friends who have been taught that. Now they can still fly, and kind of the idea is that, yeah, it's physically incorrect, but okay, maybe you don't need it to still be able to fly the plane, so we'll spend more time on leadership and things like that. But that is absolutely not what happens. So, and I think the idea is that because this is a continuum up here, the idea is that those two particles adjacent to one another must have to then meet up at the trailing edge to not have a ripple in the ether or something like that. But what actually happens is something a little more complicated. So this is showing a set of streamlines. This is from Holger Babinski at the University of Cambridge. And at the end, he's going to actually pulse the wire, and you're going to see that the particles on the bottom are going to move at a different speed than the particles at the top.
And not only a different speed, but they get to the trailing edge at a different time. They're not married. Right? There's
Right.
no... Yeah.
So first it's shown fast,
Yeah.
and then he'll slow it down. And actually, this was just published a couple of years ago. So this incorrect theory of lift has been kicked around for quite some time.
So you can see already the top ones, as it just approaches the wing, are starting to accelerate towards that low pressure region on the upper surface. This does relate to kayaks, by the way. We'll get into it. It's just a second.
So if we were to freeze it, it would look something like this. And if I have a set of streamlines here that's moving around, and we know in nature that things tend to move in a straight line until they're acted on by a force. So if something deflects downward, it means that there must be a positive force, or pressure in this case, down here. Likewise, there must be a lower pressure up here, and so it's this pressure differential that's going to give us that lift. That's about as complicated as it really needs to get.
And so here's a couple, 3 videos of what you might look at and say, oh, it's an airplane wing, but when I see this, I see either a hand sticking out the car window as I'm cruising down the road on a nice summer day. Alternatively, I can see that as, I've got my blade, and I can stick my blade in the water, right? And if you're cruising along like this, and I stick my blade down in the water this way, right, I can twist it back and forth and feel an effect very much like this. So here, my blade is slipping as straight through the water, which is of course hard to do, but you can get your blade to slip straight through the water, right? You get it, crack it open just a little bit, right? Just like your hand outside the window, and you feel this lift force, right? Why is that? We're forcing these air molecules to change direction, right? And that requires some force. The force pushes back on the blade, and that does something for us, right? But as Doug said, it comes at a cost, right? There's some losses there. There's a little bit of drag, right? And you're thinking, oh man, my side slip or my hanging draw is getting pretty solid, and so I'm really going to open it up. But what happens then is you start to lose all the effectiveness, and then you just put on the brakes, right? And you got to learn to feel that. And imagine what's happening. Can the water make it around both sides of the blade to make me do what I want to do? And that's what's really going on when you do these ruddering strokes.
So at 0 degrees, you may not have any effect. 15 may be optimal, somewhere in between, and then at 20, you're just slowing down. And you're still moving sideways, but it's going to be a short ride.
Yeah, so to make this a little bit more real, and to spread the wealth around, Lendl paddle here, so we promote the Warner paddle here. This is actual calculations, right? So for every degree that I open my blade up in the water, for every degree of angle of attack, I gain a little bit of lift. all the way up until 10 degrees, and I can get, I'm on a keyless blade, if anybody's paddled with a keyless big foam core carbon fiber blade, 15, 16 pounds of lift coming off that blade when you plant it in the water. And this is at 3 knots, I think, yeah, at 3 knots up there. Right, so that's considerable force that the water, is pulling or pushing on that blade. If you put it right to your side, the boat moves sideways, right? But if I apply all that force up by my bow, right, that's gonna move my bow. If I put my blade way back here and do the same kind of thing, I've got 15 pounds pulling on the stern in that direction, that's gonna move my stern, right? Bow rudder, stern rudder, side slip. Oh yeah, here we go, Roy.
Being quiet.
Yep. Right. So this comes up a lot, right? And Roy came in here ready to sit on his hands, and he's not going to sit. But this comes up all the time, right? Oh, dress, which one is better, the Greenland stick or the Euroblade? Which is better? Which is better? Which is better? To which, and I do this to my students all the time. I don't answer any questions, just ask them more questions. So I'll ask you a question. Can you do the next one?
Oh, yeah.
Yeah. Which plane is better? Right? Well, it depends. If you're a farmer in eastern France, in the late 1930s, I bet you'd be a pretty big fan of the P-51, right? But if you are, trying to get around the world on one tank of gas, you're going to pick a drastically different plane, right? So, which is better? Crazy question. They do different things. They have advantages and disadvantages. How do you even measure efficiency? How do you measure effectiveness? How do you measure any of this stuff? Too complicated, right? So
And it turns out that the wetted area here is almost identical to what it is here. All right. So it's two different.
They're more similar than they are different. They both fly.
So here's our first myth. And Greenland people don't even have this luxury. But how many people have heard that if you feather your paddle, or if you don't feather your paddle, lack of feathering a paddle, I'm going to be in, say you're the wind and you're blowing at me, and I have a 20-knot wind, boy, I'm putting a huge amount of drag and stress because this is a pretty bluff body moving through the air. So why not better put like a nice 60-degree feather, and I'm going to slice nice and smoothly. We can see that visually here because here's our nice feathered paddle, and here's our silly unfeathered paddle, and boy, there's a lot of drag force on there. It's a bluff body. Of course, the problem with that argument is that what happens if now I'm paddling this way, and now I'm going to be getting that tremendous amount of lift or drag going in this direction. And the reality is that we don't just paddle upwind or we don't just paddle downwind, but we paddle in some kind of combination. And as we can see here, we don't have any sort of bluff body. It's somewhere in between for all these other parts. So there are reasons perhaps to feather your paddle, and there are reasons perhaps to not feather your paddle, but they have nothing to do with the drag that you're actually going to have on your blade.
Yeah, so drag is one of the advertised topics, and it's one that's near and dear to my heart. I studied drag for many, many years. Does anybody know kind of the 3 types of drags that might affect us when we're out in the water? It can be roughly categorized in 3 spots. Does anybody have one?
Skin friction.
Skin friction. Yeah,
Skin friction
right.
will be shown here.
Right. So that guy's working pretty hard, and he's dragging some water along with him. The water's stuck to him, so he's moving some water. Yeah, what's another one?
All displacement.
Yeah, the pressure drag.
Pressure
right?
drag. So some smooth flow up here, and then something else behind that.
Yeah, that water behind him is definitely disturbed. Yeah, Doug, you want
No, that's the next slide.
Oh, next slide. All right, yeah, right. And there's a third?
We'll have fun with that.
Yeah, we will.
And the third one, this
Wave
one's a little
drag.
bit trickier.
Yeah.
Wave
drag.
Wave drag, yeah,
Right.
exactly. And
So
the
when
water tends to kind of pile up here on the front of the boat, and you have to punch through that. And ultimately, that's going to limit what your top speed is going to be.
right. So one way is there's a big wake on the next page, right?
Yeah.
Yeah. Right.
Oh, no.
Oh, at 3 o'clock this morning, Doug and I are like, okay, let's do this one first. Let's do this one. So this is a pretty sweet little slide. What it just says is how are these different aspects of drag contributing to slowing us down at different speeds or different lengths of boats. And viscous is the skin drag. The water is stuck to me, I have to pull it along with me. Form drag is I'm disturbing the water behind me. And wave drag is I've got this wave, these waves that are emanating out from my kayak, right? When they go lapping up on the beach or the riverbank, Splash, 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 splash.
The
That's
water's piling
energy.
up on the front.
Yeah, I mean, that's energy. Where did that energy came from? Lunch, right? That's you that made these waves splash on the shoreline, so that's,
So to see where we exist as kayakers, we can do a little thing here where we're just going to compare the length of the boat and how fast it goes. So that's just a parameter. And we can add in some things that we would recognize. So for example, us in a kayak, this would be a typical sea kayak, would be somewhere right about here. So we're dominated by viscous drag, a little bit of wave, and then some form. If you're on the other end of the spectrum out here in a surf ski, perhaps, you're going to be really at the upper end of what that wave drag can do, and it's going to be a much greater fraction. In fact, it's off our chart here. And the form drag is going to be a lot smaller because you're a skinnier boat, of course.
yeah, and one thing to notice about too that's confusing about this is that it's not like your skin friction drag is decreasing as you go this way. I mean, the faster you go, there's more of all kinds of drag. It's just what fraction of it, right? It gets to be roughly a third, third, third. But the USS Enterprise, right, has a lot more drag than your kayak, right? It's just what fraction of it comes from what component.
So the distribution, what we face as paddlers. So here's the slide that you wanted.
Oh yeah, yeah. Go ahead, Doug.
So this is a fun one, and this is our second myth that we hope to debunk. So if you walk away from this and you only take maybe 3 or 4 things, hopefully these myths will go with you. A commonly said thing is that if I'm punching through the water, that somehow the water behind me is loose ball bearings. That somehow I have this loose aerated water, and up front I have this really tight water. So the tight and loose water thing comes up quite a bit. But what we're actually seeing here is just profile drag. So it is true that right in front of my bow is going to be some higher pressure, and right behind is a wake. And a wake would be what we'd feel you can draft on a bike, or you could draft behind like a semi-truck or something like that. But as we said in the beginning, in fluids, I can't take the air and squeeze it or pull it apart. I can't disassociate these molecules here just from my paddle. So in fact, the air that's, or the water that's in front is of the same spacing as the water behind. It's just that it has a higher pressure. And it's that pressure differential, in this case, that is creating some resistance and is creating drag. So if you hear somebody say that there's tight water in front of my bow, loose water behind my stern, politely debunk that and say, no.
Politely. Because there are nice people that say that.
Now we're on to myth number 3.
Yeah, and this is kind of a fun one too, and some people have alluded to it already. You know, should I buy a longer boat to go faster? Longer boats are faster. Who has heard that a longer boat is faster? Right? Of course, because they are, right? And you read it on paddling.net. So right? Okay, so but,
You plumb bow too.
yeah, right. So I asked my son about this. He's 3. So he summed it up for me. He said, yeah, here's how it goes. It's this hull speed. He's hoping he doesn't get the same thyroidal cartilage I got. So. But I thought, well, Wally does a pretty sweet job, but I can do a little better than that. And so we have this little image here, right? Well, what's going on? Doug and Callum stressed many, many times, right? Longer waves go faster, longer waves go faster, longer waves go faster. Well, if you're, whoops. Yeah, there. So if you're pushing some water along your bow, right, that wave goes as fast as you do. So it works the other way around too. Faster waves are longer. So if you go faster and then faster, look at how this bow wave that you're creating gets a little bit longer and then longer. Now right here, this is kind of an interesting spot because my bow is sitting up on the crest of my bow wave, and my stern is sitting up on the next crest of that bow wave, right? Exactly 1 lambda, 1 wavelength past. And if you start to go a little bit faster and force this bow wave to be a little bit longer, what happens? And you notice anything different about this boat, this boat, this boat, and this boat here? Anything interesting?
That one should squat in the back.
Yeah.
So to go any faster here, you're simply going to be climbing up that wave.
Yeah. Literally, you got to go uphill.
So
To go any faster than that, you got to start.
You may have heard the term hull speed, so this is what we refer to when we say hull speed.
Yeah. And so my good friend and videographer Aki and I were talking about this yesterday. And it's not like it's a hull speed, like it's some, like the gel coat peels off the fiberglass as soon as you hit the hull speed. But it just gets much, much harder to go any faster. Right? That's what hull speed means. Oh yeah, great question.
What happens when you trim the boat out and you make the bow
Oh, heavy by an inch or
Ooh,
so.
okay, we have that coming up.
Yeah.
Yeah, that's a couple slides. You're very astute. You're a couple slides ahead of us. We do talk about that shortly.
Okay.
So the takeaway here, though, is there are reasons to buy a longer boat, hold more gear, you can track straighter, and maybe if you're paddling all day or racing, you might notice that there's a speed difference. But the maneuverability and the other factors, there's no accident that in sea kayaking in particular, you're seeing a trend towards shorter boats. They're fun, you can definitely keep up with your friends who have 16, 17, 18-foot boats, and the reality is that none of us are really approaching what this hull speed is, unless we're a competitive Olympic K1 racer.
Yeah. So it's you know, a lot of people tell you got to get a longer boat, and they have a higher hull speed for sure. You can paddle a 20-foot surf ski faster than you can paddle a 14-foot pungo. However, I don't spend a lot of my paddling days going much over 3 or 4 knots, right? We've already talked about that. And so if you look at the wreck boat that's 14 feet long, the hull speed, 5.02 knots. Right? CD Extreme, right? One of the longest of the touring boats that are out on the market. That's not even on the market anymore. A whopping 0.8 knots faster than that, right? It doesn't make a huge difference. And so the question.
And most of us are not even paddling in
Yes.
this
And that's the
realm
ball.
on a
And
regional
that's what,
paddle.
yeah, that's the wall, right? It gets much, much harder to paddle any faster than this, right? You can do it, you can get over your hull speed a little bit, but it takes an enormous amount of energy to get that. So the question is then,
So this is the question
Oh,
of trim.
yeah,
Yeah.
We could do one more. We could do rocker where you've only got a 14-foot.
yeah, 18-foot boat,
Board with a
right?
14
Oh, that's a
foot.
very good point. And we should say that we're talking the wetted length here.
The water line.
So the water line, and if you have a lot of rocker, you may have a good 1.5 or 2 feet that are not even touching the water. So we're not counting that.
So, you know, stability was one of the promised topics of the day. So we'll talk a little bit about stability, right? If I want to make my fastest boat possible, surf ski, K1, C1, a rowing shell, right? They have this perfectly round or semicircular cross section. Why is that?
That's why it's
Minimal skin
That's what it is.
friction.
Yeah, it's the least surface area for the same amount of displacement. We have to displace water to float, and so this gets us the least wetted surface for the same displacement. Right? However, that comes at a cost. You put a K1 or a rowing shell in the water, and they tip over. Right? It doesn't even sit there, they just tip. So the flip side is a nice stable boat like this, right? It always stays nice and parallel to the surface of the water.
So this would be a pungo.
Yeah, this is their point, right? But in big swell, you don't necessarily always want your boat parallel to the surface of the water. You want to be upright.
Yeah, this is stability in flat water, we
Yeah.
should say. It's a different situation in waves.
So, you know, we come up with a nice compromise, right? It's got some of the stability back here, the hard shines down here, but yet has a somewhat efficient hull shape, you know, to minimize wetted surface for the amount of displacement that we need, all right? So what happens if, say, a 110-pound paddler hops in the CD Extreme? You know, then we wind up with something like this, right? Here I've got the compromise that I was after between the fast and the stable hull shapes, right? But if you have too light of a paddle in too long of a boat, they don't sink it enough. So the nicely compromised hull shape looks an awful lot like the stable hull shape. But they don't even get the benefit of the stability, right? They just get a lot of wetted surface for a little bit of displacement and not going any faster because you're not going to go much over 5 knots generally anyway, right? Just this summer at the symposium, my 67-year-old neighbor went on an open water adventure with us in a little 14-foot sailboat, right? And had no problem leading the charge 2 miles out, 2 miles back, open water conditions, in her 14-foot boat, right? No problem. Right? If you're going to spend some time worrying about this stuff, get your butt in the boat and paddle, rather than calculating the hull speed that we've got. What's the next here? Oh yeah. Oh, this is another one. Right?
So this could almost be a whole half-hour talk. We'll try to condense this down into about 5 minutes. Sorry?
I wanted to ask this.
Hold on.
Okay, good, good.
You got a question about this?
No, he wanted to ask it.
Oh, you did want to
This is
ask.
the question that he brought.
Should I polish my boat to go faster? We considered, should I listen to the guy on the late night cable with the Australian accent, like hawking miracle stuff? Because the one Australian guy died, and they got a new Australian guy to sell the stuff. So that's, so there's a really, really important video here, and it's a concept in fluid mechanics called no-slip condition. That is this molecule of water. Right? this molecule of water that's touching your hull is stuck to your hull. And there's nothing you can do about that. It doesn't matter if you use PAM, or Crisco, or wax, or Teflon, or just organic lard, it's stuck. Yeah.
What about the golf ball?
Oh yeah. That's a great question, and because it relates a little bit to the shark skin. We'll definitely talk about that, but that has to do more with pressure drag than skin drag, believe it or not, right? And that's one of my favorite topics as well. So you can see that there's some water, right, that is always, regardless of coating and sanding and polishing, stuck to
And the
it.
evidence of this is simple. If I take a board and I dunk it in the water, I pull it out, it's wet. There's water that's stuck to the surface. So that's the no-slip condition.
A better example would be dust
Right
on your
along the
fan
surface.
blades.
Yeah, yeah, right, because
Why
it
does the
never
fan
gets
get-
windy there,
Yeah.
because that air on your fan blade is always
Skin
stuck.
current.
Yeah, excellent, thanks, Jeff. So yeah, and anybody know the name of this little region that's,
Boundary.
wow, yeah, the boundary layer.
That's nice and good. There we go.
Okay,
Yes,
so that's
it's the boundary layer.
Yeah, and that's what Doug and I both studied boundary layers a lot,
Yeah.
right, over many years. Yeah.
So does the condition of the boundary boat affect the boundary layer?
Yes.
Oh yeah, so the question, right, back to the question, should I polish my boat? Right, okay, so let's keep going.
Yeah. So just keep this in mind. There's this region that's influenced by the wall, and we're going to call that the boundary layer. That's
And by the wall, in fluids, we call it the wall, right?
Yeah.
Whether it's the ground,
Yeah.
or the hull, or the whatever, we just call it the
This
wall.
is going to be the hull of our boat here in this case.
And if we look at that a little bit more closely, we get into some turbulence, right? And not turbulence like put on your seatbelt and you know, finish off your cocktail, but turbulence like little bitty eddies, like little swirls of fluid that are, you know, around the surface of your boat. But you get down close to the hull, really close to the hull, and there's no room for those swirls, right? There's this sticky, viscous, syrup, honey-like fluid that's stuck down really, really close to your hull.
We're going to call this the viscous sublayer.
Yeah, and that's called the viscous sublayer. And that's, do we want to be sticking things up into this high velocity turbulent water? No, not really, right? But if it's down there in the laminar sublayer, the viscous sublayer,
It's going to have no effect.
yeah, it's stuck, right? So the question is, how big is that, right? And so this is an actual calculation too. And this is for, I think, 3 knots again. And so as you move back from your bow, that boundary layer gets a little thicker, but the viscous sublayer, right, is on the order of 100 to 150 microns. Right? Anybody have a feel for what 100 microns is like? How big is 100
Thickness of
microns?
an air, thickness of hair,
Of
of a hair.
a hair? Yeah, a little bit thick hair, right? And some of coarse hair, right? Sheet of paper?
Yeah, there's about 50 microns, I think.
Right,
Okay,
yeah. Mine sometimes feels like 120, 130. right?
Mine's a lot thinner.
Yeah, yeah. Yeah, mine's gray. Yours is gray.
Yeah.
So it's this thickness here, and then the question is, because still we haven't, and what's your name?
Ben.
Ben, yeah, Ben still wants to know, what the hell, man, how should I sand my boat? So, this is, you know, typical grit size sandpaper, right? So these are the ones you can get at your hardware store. And this is the size of the roughness that you'll get out of that, right? Remember, we're looking at 100 and some microns thick, right? As long as we keep things smaller than 100 microns, you're in pretty good shape. Which means you can use some pretty rough paper, right, to be polishing your gel coat. Now, to be safe, you want to get it all the way down to, say, 10% of that, 1/10 of that, then you can go to 220, right? And if you want to be able to comb your hair while looking into the hull of your boat, right, go crazy, 1200, polishing, you know, wax and buffing, whatnot, but it really won't make you much faster.
So don't go over 220 unless you're retired or you're just
Yeah.
obsessive compulsive.
Right.
Okay, so then the last thing, this is a subject that, you see the Beloit Pesh? No? Okay.
Back to shark skin.
We had
Yeah,
a,
we'll talk.
we had a discussion about this. If you've ever been paddling in a tidal race, have you gotten to a place where you get shallow and all of a sudden it feels like I'm paddling in honey and it's super, super viscous? Well, what's going on with that? We thought it was the boundary layer, actually. That was our initial thought on that. But doing a little more recon on this, it turns out that, remember that first slide that we showed that had velocity related to pressure, and we know that when velocity speeds up, pressure goes down. And so what happens here is that we're in some shallow water and we start to get constricted. So because we're in a lower area, the velocity has to speed up. pressure goes down and it actually sucks our boat down. And it turns out that this is actually a velocity squared type effect. So if we actually start paddling faster, we're just pulling ourselves down a factor of 4 or more. And the result is going to be an increased bow wave here and an increased wave at the stern as well. And it's actually called the squat effect. And you can imagine if you do a Google search for squat effect, you're going to find a lot of really crazy pictures.
Don't do it at work.
Definitely put your filter on before you start to But it looks something like this. So we actually start to paddle, and if you're in this situation, you can paddle harder and harder, but you're just going to get thicker and thicker, and it's going to be more frustrating. So hopefully if it's a tidal race, you can just kind of ease back and enjoy the ride and cruise through. But you will actually get, and the squat effect comes from the fact that the stern will squat slightly, and that will of course make your body rise a little bit. But paddling faster won't do anything for you. It's almost like quicksand would be maybe a better analogy than honey.
So it's not what they sometimes say, which is the reflection of your fresh wave off the bottom back into your boat.
That's what it feels like.
It's a secondary effect, but you will get some interaction here, but the dominant mechanism is that you're actually drawing the stern down. So when you're drawing the stern down, of course, your wetted area is getting faster, and the velocities are increasing, so then the profile of the friction drag is increasing as well. So we're getting more wetted area, higher velocities, more drag, and it's all going up by a factor of squared, so twice as fast, 4 times the effort.
So a lot of questions.
Yeah, so I think at this point, yeah, we need to do a quick thanks, and then we'll get to the questions, because we saved plenty of time for questions. We do want to thank, well, I'll let you do it.
Yeah, so Nancy, we've been kind of pushing this for a long time, and then after Door County this year, Nancy's like, yeah. And if those who know Nancy, she just kind of walks up and says, I need this at Canoecopia, and then she kind of walks away and goes over.
I already looked in here to make sure.
Yeah, I know. She doesn't trust me at all. But yeah, Nancy and Darren and Sasha for putting this whole thing together was awesome. Everybody originally, Greg and Callum. Greg didn't want to do this, and then we had an 8-hour drive up to Doug's wedding and then 8 hours back. And by the time we got back, man, Greg was on fire, ready to go, and put together a great talk too. And then our wives who've been putting up with us talking till 1 and 2 in the morning.
Little Skype days.
I thought you were skiing.
Last week, but-
there were questions about shark skin and golf balls and
Trim,
Go ahead.
Trimming the nose heavy.
Oh, the nose heavy. Yeah. Doug, you want to take that one? So, are you talking nose heavy as a way to reduce the?
Trim.
Yeah.
The
So,
boat knows everything.
there's a number of reasons to trim it. Oh, yeah.
so when you're increasing speed,
Yeah.
you get that bottom drag affecting you.
Yeah.
So if you put more weight in the bow of the boat
Yeah.
and get it to trim,
Yeah.
you're gonna lose that. So even on a canoe trip in Canoecopia, we worry about the trim of the boat so that you have more speed with the same effort.
Yeah. Yeah.
And the other thing, I used to race canoes, and in shallow water, if you get it going fast enough, it'll pop and it'll start planing.
Mm-hmm.
And I could do it at a foot and a half, but the really good guys could do it in 3 or 4 foot of water.
Yeah, so that's the difference between a displacement hull and a planing hull. It doesn't break, right? But it gets much harder. But if you can get that boat up on top of that bow wave, then that's planing. And then you're in a completely different regime. Yeah. Shark skin briefly, right? It's easy to make fun of loudmouth Australian guys on late night cable. But there are things, that make things go faster. Sharks.
So riblets.
Yeah, really. But we never put a picture of riblets on it, did we?
Yeah, but
Oh, yeah, right. So we can talk about this. The whole reason I went into fluid mechanics in the first place is in 1987, the America's Cup boat, Dennis Conner, put these riblets, like those rulers where the picture changes, you tip it back and forth, those like little grooves or like a record. Well, he wrapped his whole boat in these things called riblets. And what they do, so it worked in 1987, and then it was banned from sailing that following year, and then it worked for the rowing in Olympics in 1992, banned from that. So as soon as you start banning things, it's like, yeah, that's a pretty good sign that it works. But it wasn't until recently. What's that?
Swimming.
Oh, and swimming too. Yeah.
2008.
There are definitely some things that work, and it wasn't until just recently. Joe Katz at Johns Hopkins. What's the guy? Chechio, right? He's done some of this. Cessio.
Yes, that's it.
Cessio, yeah, at Michigan. So what they do basically is, this picture shows all these little vortices spinning kind of this way, right? But there's also some that go this way. And they convect or advect this really high momentum fluid, which is, if you imagine the water flowing by the kayak instead of the other way around. These vortices like this bring some of that really stagnant fluid down close to your hull. That's bad. And so what these rivulets do, these longitudinal little grooves, is they inhibit these vortices from forming. And then, hence, thicken this viscous boundary layer a little bit. Because while the viscous boundary layer is thick and honey-like, it's better than the real stagnant fluid that's out farther away. And that's how those rivulets work. Sharks have them, beavers have them, otters have them. They show up in nature a lot, and I think that's where the idea came
So
from.
it has to be lines? Like,
They run
Yeah,
parallel?
and it only works, so they have to be streamlines, right, they go the long way. And it only works at certain speeds and certain densities and certain viscosities. So they have to be very fine-tuned. So on a K1 or C1 or run course where you pretty much know this boat is going to make it down the course between 5 minutes and 26 seconds and 5 minutes and 28 seconds, right? Very controlled kind of conditions. They work well. On a sea kayak where you're going different speeds, different conditions, different water, they wouldn't really be that effective. Golf balls very quickly, we've got some cool pictures here to show a golf ball. But basically, there are these two kinds of a golf ball flying through the air isn't on the surface. There's no wave drag, right? So that limits to two factors. That is skin friction, right? The stickiness of the air, and then are you going to find that those pictures? There's a couple under. They're in the CD there too. But so. So imagine there's a golf ball flying this way, right? And then or imagine a golf ball like this and the air is moving this way. As the air goes up and around the golf ball, it has to go faster, right? It has to get out of the way of the golf ball, so it has to go a little bit faster. That means the pressure is lower, right? But as it kind of comes back around the backside of the golf ball, it can slow down again, and it's higher pressure. But wait, if there's higher pressure here and lower pressure here, it doesn't seem like the air should be going that way? But we just said it's going this way. That's a problem, right? That's called an adverse pressure gradient. And it turns out a turbulent boundary layer with all the little swirls, bringing some of that high momentum fluid down close to the surface of the golf ball, right, is able to more easily overcome that adverse pressure. So we want momentum in this case. And they discovered that, I think it was in Scotland, that like the poor guys with the old beat up golf balls were just beating the shit out of the rich guys with the brand new golf balls. And they're like, what the heck is going on here? And then it was discovered that, sacrificing some skin friction, right, was worth it, because then you have less pressure drag. And that's why the dimples, and they're very carefully calculated to work at certain Reynolds numbers, certain conditions. And so it's a trade-off, but you're actually inducing turbulence to reduce the net. Yeah, so perfect. And then they trip it. I think the velocity increases, and you can see the size of the wake with a smooth laminar thing versus, so this, Greg was really good at this. It's like being a weather guy. So here, I mean, the pressure is increasing here, and so the pressure wants to push the fluid that way, and this air is trying to flow this way, so it gets screwed up. And so by inducing this turbulent boundary layer and getting a little more momentum down close to the surface, it costs us, right? But that momentum helps minimize the size of the wake. Really big wake, right? But low skin friction, drastically reduced wake. And we paid a little bit for it with increased skin friction.
I realize this isn't the physics of golf, but doesn't the golf ball have to be spinning for that to happen?
No, that's what caused it to.
Well, that's you've been seeing my game.
Yeah, straight and narrow every time. Yeah.
If you can get it spinning, you'll give it lift. That's
Right.
the key thing there. So this would be the no dimple golf ball, in case people miss this, and this would be the golf ball with dimples.
So does this apply to like skin on frame kayaks with the variation, from the fabric, like with all the little spurs or circular?
Well, so keep in mind the size of the golf ball, right? It's possible that the golf ball could have laminar flow going all the way around it, right? By the time you're a foot off the bow of your kayak, it's turbulent, and there's nothing you can do to make it not turbulent. So that doesn't really have the same effect on something as big as a kayak. Right? Sometimes you'll see on airplanes on the leading edge of the wings, you got like one of the nice comfy exit row seats. You'll see on the there's a little tripwire, just like this on the leading edge of the airplane, intentionally to induce that turbulence, so the wing can go at higher angles of attack and not stall. I did a brief foray in aerospace engineering, and so I learned about this kind of stuff.
You don't want to put
lots of great.
dimples in your kayak, is that what you're saying?
What's that?
No dimples.
No, the dimples wouldn't do any good. And the Mythbusters did that, right? They put the dimples on the car, and
Yeah,
and they actually got.
you got 10% better mileage.
Yeah, right. And I saw that. I'm like,
When the
I
core-
don't know about that. Yeah, Brian, what?
We talked about how you can only polish your boat so much to 110 microns, and after
Yep.
that, it doesn't make a difference. So does it not matter if you have a polyethylene boat or a fiberglass gel-coated boat?
Yeah, excellent question. So the question is, if anything smaller than 100 microns doesn't matter, well, anything smaller than 100 microns doesn't matter as much, right? You get below 100, get below 50, and you're pretty safe, right? They're diminishing returns. Polyethylene boat versus gel coat. I'm a fan of just get out and paddle, right? And most of the scratches, you get a big deep gouge from landing on like a barnacle covered rock or beach or something like that. Yeah, those will slow you down, right? But just get them smaller than a sheet of paper, and it's going to be just fine, right? The big advantage, in my mind, of a composite boat, gel coat, fiberglass, is it's repairable, right? You can hit the beach and fix it. Polyethylene boat is harder to fix.
Harder to break, too.
Yeah.
Plastic welding.
Are you going back to the plot?
Yeah.
So that's Wally right there. That's him. He was telling me about the hull speed. Oh yeah, another one, Tom. Yeah.
Chris, just, I was taught that, now I'm talking about paddles, not about boats.
Yep.
And I'm a canoeist, not a
Yeah.
kayak.
Yeah.
The catch is a paddle.
Yeah.
And I was taught that if you drop your blade down into non-turbulent water, that you have a less slip on the stroke, you have more efficient stroke.
Yeah.
We'll
Yeah.
have to do that next time.
You want to
Yeah.
bust that?
So about 3 weeks ago, Doug and I were having a nice chat at lunchtime, and it got a little heated. And I opened my door, a bunch of students waiting for office hours, you know, and all their eyes were this big, because their eyes were flying, right? And I'm like, no, he's really a good friend, right? We're great friends, we just disagree on some stuff. So how does, how
It's
does
easy to
this...
control with a canoe paddle, maybe not so much with the.
Oh, yeah.
You know what I'm saying?
It's...
Yeah, he's talking about punching in V or.
Right.
Yeah.
We do not agree. Doug and I do not agree, and the people we talk to do not agree on exactly what's going on there, right? Certainly, these two blades do very different things. They have, well, not very, they paddle, right? They move the boat. So you're saying, plant the blade outside of the boundary layer, right?
Well, not so much, but when you make your catch,
Yeah.
then you drop the blade so that the face of the blade finds cleaner water as it goes down.
Is that looser water or tighter water? Is it third category?
We call it green water.
I mean, does the-
Rubber green water.
Is there anything to that? or-
I got nothing for you, Tom.
Can you get on that?
Let me comment.
He's going beyond the aerated water to green water.
Right.
If you put your paddle in the water,
Yeah,
and it goes down a foot,
yeah,
and you pull it straight back,
yeah.
as soon as you start pulling it back, there's water going around that blade.
Right.
And so there is a pressure wave that's going in front of the blade, just like that ship had a wave that was in front of it. Or if you're pushing snow, the snow piles up in front of the blade. That's not a good example, but there is a wave that's in front of the blade
Definitely.
as you're pulling it
Yep.
back.
Yep.
And I agree 100% with him. Go ahead and put your blade in the water and pull it straight back and
Yeah.
don't go any deeper.
Yeah.
Next time you're in a canoe, try to have about 4 or 5 strokes, and then the next stroke, put your blade in, and as you're coming back, go deeper and deeper and deeper. And that bottom inch of the blade is experiencing no pressure wave in front of it, and you're catching clean. The swimmers do the same thing. They don't come back with a straight stroke, they come back with an S stroke.
They
Because
scull,
they're always
right.
looking for
Right.
water that's not been disturbed. And the same thing in sailboats, you're always looking for clean air.
Yeah.
I agree 110% with this guy, when you paddle, if you want to be efficient.
Tom's got a friend.
I never met this guy before.
He's a plant.
You go deeper, you're gonna feel it's harder to pull that paddle back.
Yeah, and I agree completely. And you plant the blade differently at different angles, yaw, pitch, and roll angles.
I'm
You have
talking
different.
about straight back.
You different shape. And
Greenland
Doug
paddle.
and Jeremy, we don't necessarily agree, and we've always talked about, yeah, let's get some cameras out and get some video, and get some good images. But
The only way
so what
you're
you should do,
gonna-
here's what you can do. Here's a great idea. Go on Canoecopia.com and say physics was awesome. We got to do it again next year. Fund Doug and Dress, and they'll do some experiments.
What you do is you put the stress sensor in there,
Yeah, right.
and you measure
Yeah, put a strain gauge on the shaft.
strain gauge on the shaft, and you'll find it out. That
Right.
you're gonna-
Yeah, there's a lot of cool stuff that we could do there. I don't have.
Next year.
Yeah. Next year. Look, yeah, I think we have time for one more, because Nancy said 8:50, even though we're the last talk, Nancy wanted us out of it.
And we will continue this at the plaza.
At the plaza, yeah, we're going to the plaza at talk more.
All of the famous plaza.
Yeah, right, we'll agree.
How many times have
Tom and I gotta still be friends after. So one more question. Jeff, yeah.
Okay, so I've been a technician for 35 years in the medical industry, technician. And what I say the difference between the technicians and the engineers is you guys dream up that stuff, and we're the ones that gotta fix it. Hold on, let me connect the dots here. And I know you can't disagree with me. The real answer lies in putting your butt in the boat and
That's right.
just putting on hundreds and hundreds of miles.
Right. And these mock-ups would never have been made if it weren't for guys like you.
But we, yeah,
Exactly right.
but we still, as a technician, we still have to know the basic principles. We don't have to know the math. We get out and we prove
Also,
it.
the rocker in the boat changes when you're on wave.
So I thought it was awesome.
Oh, cool. Very
Yeah.
good.
Could go from a 14
No, that's a really good point that you
water
bring up.
changes the whole.
So we hope you learned something from this, but if you didn't, if there's no takeaway, you'll still get out and have fun. This is just for,
Oh.
but what what we are offering up is some ways to think about things that might help you save some time, save some money, and save some effort. So with that, thanks for coming.
Yeah.